Okay, today we're going to go over ions. So first, let's go ahead and just define what is an ion. I know you guys defined it in your homework, but just so we all have a definition to go off. Okay, so an ion is going to be, so we'll define this here. It's going to be an atom, or group of atoms. We'll see examples later. Or group of atoms with, abbreviate here, with an electrical charge. Okay, so it could be, we're mostly going to study atoms, but they can also be groups, which we'll see later on. Okay, and the reason that they are electrical charge is due to either losing or gaining electrons. Okay, so let's look at an example of that. So let's look at sodium. So we're going to look at sodium, which has atomic number 11. Okay, so if we look at the periodic table, we have sodium is here. Okay, number 11. So if I draw the Bohr model for sodium, the Bohr model is going to look something like, in the inside we have 1, 2, and 3 energy shells, right? We have 1, 2, 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7, 8. All right, so we have a total of 10 here, and then 1 on the outside. So sodium, even though in this example we're not showing the inside nucleus, the protons and so forth, it is there. Okay, and sodium has 11 protons, and it has 11 electrons. Okay, so the total net charge of it is going to be 0. So it has no actual charge, right? However, we have discussed that sodium likes to lose 1 electron, because everything wants to lose or gain electrons to become full, in other words, to have a full outer shell, because that allows it to be stable. So if sodium were to lose this electron, if they were to lose an electron, what would end up happening is we would still have 12 protons, but now we would only have 10 electrons. So if we add that up, that gives us a total charge of +1. So that's why sodium forms a +1 ion. Positive, we also call positive ions cations, which we'll define in a bit. Okay? All right. Let's look at another example here. Let's look at oxygen. So oxygen has 8 electrons. It has 2 energy shells, and we have 2 here, and then 1, 2, 3, 4, 5, 6. Okay, so it has 6 electrons in the outside, 2 in the inside. All right, so for oxygen to become full, there's 2 possible ways. It can lose all of these outside electrons, or it can just gain 2. Okay, in terms of energy, it's easier to gain 2 than it would to lose 2 electrons. Also, oxygen has a high ionization energy, which means it's very difficult to take off those outside electrons. Okay, so it's going to gain. So what oxygen does is it gains 2 electrons. Okay, and before that, usually oxygen, before we go over it gaining, let's look at the number of protons and electrons. So usually it has 8 protons and 8 electrons for a total charge of 0, right? However, once it gains those 2 electrons, we still have 8 protons because it's still oxygen, but now we have 10 electrons. Okay, we add that up, that gives us a total of -2. In other words, it becomes every electron that we add gives us another negative charge. If I were to add 3 electrons, my total charge would be -3, and so forth. Okay, so oxygen becomes a -2 ion. Okay, so we can define these as well too. So an anion is just a negative ion. Okay. The way you can remember is you can kind of remember by saying A negative, right? A negative ion. Cation. Well, you should probably know that, right? Because it's going to be the opposite of that. Cation is going to be positive. The way I kind of remember it is if you look at the actual word cation, there's a T that almost looks like a plus sign, right? So cations are positive. Okay, now let's go over whether things lose electrons or whether they gain them. So if we look at our periodic table here, okay, so everything in this first group has one valence electron. So they're all going to do the same thing as sodium. They're all going to gain one electron. So everything here forms a +1 ion. Everything in this group wants to also, they want to lose an electron. Everything here wants to lose 2 electrons to have a full outer shell. So if we lose 2 electrons, we become +2 because we lose 2 negatives. And then the trend continues. Everything here wants to lose 3. Okay? Going on to this other side here, let's start at the halogens. The halogens have 7 valence electrons. If they have 7, in terms of energy, it's more favorable to just gain 1 than it is to lose 7. So all of these just gain 1, so they have a charge of -1, and so forth. These would have a charge of -2 to become full. These would have -3, and so on. This group, it forms what we call covalent bonds, which we'll go over in more detail later. But technically, it could gain 4 or lose 4. But in reality, it doesn't really gain or lose. It actually shares them, but that's something we'll go over later. Okay? So that's kind of the trend. So we have our metals here, right, which like to lose electrons, and we have our non-metals, which like to gain electrons to become full. So let's go ahead and get that down. So we understand the trend. So again, metals want to lose electrons, and non-metals, let me do some different color actually. Non-metals want to gain electrons. And the reasoning behind this is because everything wants to have a noble gas configuration. Everything wants to be stable like the noble gases. All the elements want to be stable. So noble gas electron configuration. Okay? Or rather, the reason they do is to get a noble gas configuration. All right. So let's look at a couple of examples. Let's say I'm looking at potassium, right? I want to find what type of ion does potassium form. Well, if I look on my table, it's pretty easy because we just have to follow the trends. Potassium is in that first group. That first group forms +1 ions. So potassium forms you can either put plus, and you can just leave it like that, that's fine. Or you can put a +1. If it's not there, it just indicates that there's an invisible 1 there. But if it was 2, then you do have to put it. Okay. Let's look at, for example, another one. So let's look at aluminum. Aluminum is in the third that this group here is, right? So it's 1, 2. We skip the D block. They don't follow the trend. This would lose 3. So aluminum reacts by losing 3. Okay, and so forth. So you just have to look at the trends on the table and look at its position, and that's going to tell you whether it gains or loses electrons. You can draw the Bohr model, but we don't need to do that because if we know where it's located, we should know whether it's going to gain or lose, with the exception of the transition metals. Okay, so a couple of things we want to note. Last of all, why is it that things react the way they do? Why is it that some gain and some lose? Okay, atoms will gain or lose electrons. Okay, so atoms will gain or lose electrons depending on what is more favorable in terms of energy. In other words, atoms will gain or lose electrons in a way which is more favorable in terms of energy. In terms of energy. Okay, so that's really what it all comes out to. So it's always easier to lose one electron, for example, than it is to lose two. It's just going to require more energy to lose two. And it's always easier to gain one electron than it is, for example, to gain 3 electrons. So the less you have to do, the less energy is going to be required. So let's look at what that means. So for example, we know that both of these lose electrons, right? So this loses 1 electron, this loses 2. The reason that our first metals here are much more reactive compared to our second group is that in terms of energy, it's very easy to lose 1, but it's not easy to lose 2. That's why this first group is very reactive, whereas the second group, it's also reactive, but not as reactive as the first group. And we did go over this briefly, okay? And also, if you think about it in terms of energy, we know our metals tend to lose electrons, right? And that's because metals tend to they're on the left side of metals have a very low ionization energy. So it's very easy for them to lose electrons because it doesn't take a lot of energy. However, nonmetals, we already know that nonmetals have a very high ionization energy. So nonmetals require a lot of energy to remove those electrons. So it's easier to gain them rather than it is to lose them. Okay? And they're very electronegative, right? So they want to gain them because the extra protons are depending on which one we're looking at. Okay, last skill we have to do is, this is the concept. We also have to be able to write electron configuration for different types of elements. So let's go ahead and look at an example of that. All right, so we've done electron configuration. However, this is going to be a very similar process with a slight twist to it. So let's do the electron configuration for, let's say, sodium. So this is ion electron configuration. Okay, so let's say we have sodium. Sodium is located, if we look at the table, sodium is here, right? So if we work through the table and write the configuration, we know the configuration is 1s2. I'm going to go quick through this because we've already had a lesson on this, so I'm not going to go into detail. And we end up so for sodium, we end up here, which is in 3s1. 3s1. Okay, so if I want to write the configuration for, let's say the configuration for a sodium atom, so for an Na plus atom. What this plus means, it means that it has 1 less electron. That's all it means, right? So in other words, it would have 1 less electron. So it would be 1s2, 2s2, 2p6, and it doesn't have that last part. So it doesn't have this electron, right? And that's the configuration for that. And if you notice, that's the same configuration as the closest noble gas, which in this case we have sodium here. The closest noble gas is neon. So that's the same configuration as neon because everything wants to have an electron configuration to be stable, right? It wants to have an electron configuration close to a noble gas that can be stable. All right. Let's look at another example here. Let's say I have oxygen, right? So we'll write the regular configuration for oxygen, and then we'll go ahead and change it. So that's kind of the strategy you can use. So we're going to write oxygen is 1s2, 2s2, 3p4. So that's the regular configuration. Remember, if we have a -2, that means it gained 2 electrons. So it gains 2. If it gains 2, then we have to add 2. So rather than ending in 4, it's going to end in 6. So our configuration for this is 1s2, 2s2, 3p6. Okay? Sorry, that should be a 2p6. Okay. So if you notice, that's also the configuration of neon. So these are the same. Both of those atoms like to behave like neon. Let's look at another example here. Let's do a relatively simple one. We'll do B beryllium here, which has a charge of +2. So we're doing beryllium, which is located here on the table, right? So the regular configuration is a 1s2, 2s2. But since it has a +2, that means we lost 2 electrons. So we lost these 2 electrons. So the configuration is just 1s2, which is basically the configuration of helium. Okay? And if we need more help, then we could do another example for chlorine here, for a -1 chlorine ion.